In this video, we demonstrate a lightweight VLC system and its application in indoor positioning. More details can be found in our Mobices 2015 paper. We use 3 demo scenarios to explain our design motivation and innovation. Existing schemes on establishing communication between smart devices and lighting lamps mostly rely on modulating light intensity. Those schemes requires increasing the pulse rate above 1000 Hz to avoid flickering. The high pulse rate, however, adds high processing overhead for resource-constrained devices. Instead of modulating the light intensity, we come out the idea to control the polarization of light, which human eyes cannot perceive. We borrow the liquid crystal and polarizing film from the LCD technologies. With those technologies, we can control the polarization of light by applying different voltages. In LCD, the backlight is first polarized by a polarizing film. When the voltage of the liquid crystal is low, the structure of liquid crystal can twist the polarization of the polarized light by 90 degrees, so that the light will pass the second polarizing film, and LCD illustrates bright. When the voltage of the liquid crystal is high, the liquid crystal will not change the light's polarization properties, so that the light will be blocked by the second polarizing film, and LCD illustrates black. At this time, our basic idea is very similar to the LCD. Since human eyes cannot perceive polarization changes, we move the second polarizing film to receiver side. In this way, the modulation can only be detected by equipped receivers. In the prototype system, the VLC transmitter consists of a polarizing film, a liquid crystal layer, a disperser, and a control board. The 2 electrodes are connected to the control board, which is continually changing the voltage of the liquid crystal layer. For convenience, we use LED lamps in this demonstration. Note that any other light, such as fluorescent light, solar light, can also be used as light source. The transmitter works by simply attaching to the lamp and facing to the light source. As we can see, the modulated light has no difference from normal light. However, if we view through a polarizing film, it can be seen that colors change significantly because of the modulated light. Our VLC design can benefit a vast range of smart devices, including those with limited computational resources. We have verified our system in wearables, such as Google Glass. But, for better illustration, we use the Samsung Galaxy S2 smartphone in this video. This is the default camera application. Similar as human eyes, the camera requires a polarizing film to reveal the modulated signal. After we attach the polarizing film in front of the camera, we can use our application to decode VLC messages. The VLC transmitter is transmitting word "hello" repeatedly in baud rate of 14 Hz, as each character is encoded in 8 bits and occupies 1 packet. It takes about 1 second to receive 1 character. The client performs localization algorithm to determine its location in 3D space. Our VLC design can be seamlessly applied in indoor localization application. When broadcasting messages of a VLC transmitter represent the transmitter's location, mobile client can localize itself through comparing transmitter's locations in the image and the corresponding locations in real coordinates. To demonstrate this, 4 transmitters are deployed as left. They are broadcasting the assigned IDs, which can be mapped to real locations. Our receiving client, due to mobility, has opportunity to receive signals from 1 or multiple transmitters. As expected, it can successfully decode them in all the scenarios. Once it has successfully decoded messages from 3 or more transmitters in the same image, the client performs localization algorithm to determine its location in 3D space. We appreciate your time for viewing our video. Thank you.